recording. As a reminder, I talked about this yesterday, but as a reminder, your quiz is open through Wednesday on AP Classroom. It is your responsibility to get it done in time. You are more than welcome to work on it in class on Monday. Monday is a work day and a homework check. When I do this next homework check, it'll only be in Unit 2, so anything that starts with a B, okay? So nothing from Unit 1. So Monday, come ready to either work on a quiz, work on any of your homeworks, watch videos, check answers, ask for help. I'm just going to walk around and bother you and see if you need me for anything. So if there's anything you need some one-on-one help with, Monday's a great day for that. If you want to bring your laptops to work on the quiz, great. You can have your laptops open so you can look at the keys on Canvas or videos on Canvas or notes on Canvas. So having your laptop is a beneficial thing anyway. So let's get started. We are doing section 2.3. It's a one day. So today we do 2.3 exponential functions. You'll probably finish your homework in class. It's a pretty easy lesson, good for a Friday. Monday we'll do the workday, and then we'll continue on with exponential functions, getting a little deeper into it in the next few sections. Okay? So, listen up. While exploring linear growth, we observed a constant rate of change. For example, in this equation, that's linear, right? X to the first. The slope tells us output will increase by 2 each time the input increases by 1. What is that saying there? Is that in a linear equation, you have a slope of 2. Rise over run, y's over x's. So as our y value changes by 2, our x value changes by 1. Up 2, right 1, up 2, right 1. Okay? Today we'll look at exponential functions and how they grow exponentially. Okay? So a lot of the same language and a lot of the same type of work that we did yesterday and how it related to geometric sequences. So if you remember, yesterday was geometric sequences and then how they related to exponential functions. We're not talking about sequences in this lesson or really any future lessons. So hold arithmetic and geometric sequences in a special part of your brain. Now we're just going to look at it as y equals a times b to the x, okay? And I want to remind you, a is your a sub 0. What's another word for a sub 0? Starting point, I like that. What else? Y intercept. And he said starting point. I'm going to call it initial amount because that's kind of what the language is used in this. So a, we just know, is a sub 0, which is the y-intercept, which is the initial amount, like in a word problem or something like that, okay? And it has the b value. The b value, if it's greater than 1, it's called exponential growth. If it's less than 1 but greater than 0, it's exponential decay. And I'll explain that better with an example in a moment, okay? But just kind of want to cover what the words are saying there. But I'm going to explain all of this as we go through the examples. And like I said, just pay attention. Let's get through the notes. Then you can work on the homework and finish it in class and not have to do this over the weekend if you don't want to. Okay, so what we're going to do is take this exponential function and we're going to fill in the XY chart. Then we're going to sketch the graph and answer a bunch of questions about it. So here they gave us some input or X values, and so I'm just setting up the problems here. And then I'm going to simplify it without a calculator. So let's start in the middle. Anything to the 0 power is 1. We should just know that. Anything to the 0 power is going to be 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Okay? Now, let's talk about negative exponents. Negative exponents, to be simplified, we need to make them positive. Okay? And to make a negative exponent positive, we cross the fraction bar. What does that mean? Okay, so looking at this, you might say that's not a fraction. 2 to the negative 2 is not a fraction. Remember, you can make anything a fraction if you want to by putting a 1 in the denominator, right? And so to simplify this, I'm going to move the 2 to the negative 2 to the denominator. When you cross the fraction bar, it changes the sign of the power. And there's nothing left on top, or you can think of it as there was a 1 there, so it's just 1 over 2 squared, which is 1/4. Now, do you really need to do all that work? The answer is no. Here's the easy way of dealing with negative exponents. Think, what would the answer be if negative 1 was a positive 1? So it's 2 to the first power, which is 2, and then you stick it in the denominator. 2 to the second power is 4, stick it in the denominator. Okay, so you don't need to pick up a calculator. It's faster to do it in your head, all right? So let's take a second. Oh, I forgot to add something. We need to add something to up here. Exponential functions, just slip it in up here, have a horizontal asymptote, an HA, that dictates end behavior. You might remember when we talked about asymptotes in last unit with rational functions, we sometimes call horizontal asymptotes end behavior asymptotes because they control how high or low your y values are allowed to go. We can stop it. All of the problems that we do today, well, I'll come back to that. Sorry, dictates end behavior. Sorry. So let's sketch this graph on the coordinate plane given to us. You're going to have to graph some little teeny tiny numbers. That's okay. They don't have to be perfect. So we have an ordered pair of negative 2, 1/4. So I'm going to go to the left 2 and up a teeny tiny bit. Where's 1/4? I mean, it's somewhere less than 1. It doesn't have to be perfect. To the left 1 up a teeny tiny bit more to 1/2. Then there's our x-intercept right there, bless you, of 0, 1. 1, 2, 2, 4, 3, 8. So those are the points. And before I connect them, because we are going to connect them, I want to point some things out to you. Yesterday we had some examples where there was a graph given to us, and it looked like that. It made like the J shape, but the points were not connected because the graph represented a geometric sequence. And remember, in a geometric sequence, our graph is discrete. It just stays like that. Just those points, we don't connect them. But in these graphs, go ahead and put in a, I'm going to talk about this in a second. There's a horizontal asymptote always at y equals 0. And then connect your points with a smooth curve, arrows on the ends. So remember I said you have a horizontal asymptote. In all of the problems that we do today, the horizontal asymptote is going to be y equals 0, always. On Tuesday and Wednesday, when we get into section 2.4, that's when we transform these, dilate, translate, reflect. When we start adding numbers in there and moving it left, right, up, down, stretch, shrink, flip, all that stuff, the asymptote will change. But today we're just getting to know the basic exponential function, and I'll just tell you, your asymptote is always going to be y equals 0. And so these, you do connect these points and make a smooth, continuous graph with arrows on both ends. But let's talk about why the asymptote is y equals 0. This is really important. Like, I don't want you guys to memorize things because we learn tons of things. Like, as you go through today's homework, you're just going to keep putting y equals 0, because it's the same asymptote every time. But why? And the why, whenever we can understand why about something, it stays with us longer. We learn it. We didn't memorize it. So we can find it in our brain when we need it later, okay? So remember what an asymptote is. An asymptote is an imaginary line that your graph can't touch or cross. So what we're saying by putting that asymptote there is something visual that I can put in words, which is none of our points will have a y value of 0 or any negative numbers. X can be anything it wants. The domain of this we're about to talk about is all real numbers. But we can't have a y value of 0 or a negative number. Why? Well, because this is where it comes from, okay? This is a picture of this. I challenge you, find an x value that you can tell me that I can plug in right there. Give me one that will give me a 0 here or a negative number. It doesn't exist. X can be negative numbers, X can be 0, X can be fractions, it can be anything it wants. There's not a number in the universe that you can give me to plug in for X that will get a Y of 0 or a negative number. So our graph has to visually reflect that, and that's what an asymptote does for us, okay? So there is no way to get that, so we have to show it, right? Like I said, the domain is all real numbers. It goes on and on, left and right, forever, hence the arrows, right? But the range isn't all real numbers. We just talked about that at length. You can't go below 0. So the way we would show this is, what's the lowest number I'm going to put in my range? 0, and it's going to go up forever. We know we always use parentheses on our infinity symbols. What will we put on the 0? Because it matters. It's the difference between a point or not getting a point on an FRQ. It doesn't include 0. So I know what you're thinking of. I made a big deal about the range in the FRQ on the last test. And I believe it was like a parabola or something. Let me just make it up. And this, let's call that 2. So the range of this one is from 2 to infinity, right? From 2 to infinity. Is 2 part of the graph? Yes. Okay. It is. It's a point on the graph. Is 0 part of the graph? No, it's all the numbers above 0, okay? So that's important. We have to know that. Because the 0 to infinity part, I don't think anybody gets wrong. We get that, but why lose a point over that symbol, okay? These next two are our end behavior limit statements. Careful, read them. As x approaches infinity. That's as x goes to the right, right? Positive infinity is to the right. Where are our y values going? Infinity. They're going up forever, right? It's pointing up. As it goes to the right, it's going up. As x approaches negative infinity, what are our y values approaching? 0. Remember, we talked about that. Horizontal asymptotes dictate our end behavior. It's always going to happen like that because you can't go below. You can't touch it and you can't go below, okay? We're getting as close as we can to 0. But mathematically, it'll never happen. But, you know, if I tried to draw this forever, it would end up looking like a straight line, right? Because our human hands can't draw it as close to 0 forever and make it look like it's going down. But it is mathematically, okay? We have one x or y-intercept, right? That would be at 0, 1. No x-intercepts because we have an asymptote there, so there would not be any x-intercepts. Would this graph hold water or lose water? It would hold it. So, what? Oh, yeah. Okay. So smart. Yes. This, if I tried to pour water in this broken bowl, it would not hold it. But if it weren't broken, it would. I was going to say it. Okay. So, yeah. If you had to choose between concave up or concave down, I think you guys would all say concave up, right? That's concave up. It's a broken bowl, so the water's not going to hold, but it would have if the bowl was whole, okay? And let's add 2 more things that they're going to ask you. Do we have any extrema and in continuity? Okay. No extrema. What are extrema, Zach, since you're ahead of the game? Min and max. Do we have a turning point? No. There's no highest or lowest point, okay? There's no sharp turn anywhere. So you'll never have any extrema. And continuity means is basically yes or no. Is the graph continuous? Meaning, are there any holes in it? No. Is it piecewise where you have a piece over here and a piece over here? Nope. This is continuous. Our pen, to make this, I never picked up my pen. I could continuously draw it. So this has continuity. Did the graphs yesterday, before it was connected, have continuity? No. Those were considered discontinuous or discrete. Okay? Next. You're going to have a chunk of problems where you have to say, is it exponential or not, and why? Is this an exponential function? So again, this is the format of an exponential function. Pretty basic, right? Not much to it. But what I want you to take away from it is that that exponent must be a variable, not a number, okay? So is this guy a function? Well, let me not get too far ahead of myself. What would the initial value in the base be here? So that's two numbers, right? And there's only one number in here. So first let's decide what is 2. Is 2, would you call 2 the initial value or the base? It's the base. Why is it the base? Because it's got the power, right? Base is the bottom number and the exponent or power is x in this case. So what would we put as our initial value, aka our y-intercept? 1. Remember, a lot of times we don't put 1 in a math problem. Like in front of an x, if I said to you, what's in front of this, you'd go 1, like duh, that's a 1x, right? We don't write it. If I asked you what the exponent is on this number, you might take a second to think about it, but it's a 1, right? It's 4 to the 1. So that's a 1. Let me prove it to you. We just graphed this one. What was our y-intercept? It was 1. It's the same problem, okay? So if you don't see a number in place of a, it's a 1, okay? And is this an exponential function? Yes, it is. It's in the form y equals a times b to the x, okay? Let's look at the next one. What is our initial value here? 4. What's the base? X. Base is the number, or letter in this case, that has a power, okay? Sorry, that's X. So initial value is 4, base is X. Is this an exponential function? No. Why not, Austin? Yeah. Remember, this has to be a variable, not a number. So that's kind of confusing because you call -3 an exponent. It is an exponent, but that does not make an exponential function. It has to be an x or an n or something like that, okay? Now let's look at this next one. We have an initial value of 5 and a base of what? E. Okay, let's talk about what E is. E is a number, even though it's a letter. So let's talk about what the word variable means. In math, when we talk about variables, sometimes we're just like, oh yeah, it's letters. But some letters are not considered variables in math because they represent a number. For example, this symbol, we call it pi, actually is a placeholder. We see it in lots of problems, but it actually means 3.14 blah, 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 right? It means it represents a number. E is a special letter that we use in special types of problems, mostly that have to do with finance, which we'll talk more about in a minute or another day. But E actually is a number. Let me show you. If I put pi in my calculator, I can have it give me the value. Okay, so there's pi. There's an E on here as well. It's right above the division symbol. So if I hit second and the division symbol, I get that cute little E on there, and hit enter, I get 2.71 blah, blah, blah. Okay? So E is the one letter in the alphabet that I can think of right now that we don't use for like algebra problems. As far as like, you know how you solve equations, and a lot of times it's solved for X, but you could solve for N, you could solve for Z. When I tell you, you can write your exponent, you can name a function, you can call it f of X, f of Z, G of L, whatever you want. We don't use the letter E because E is a special letter that represents a number. So it is the base, okay, but it has a negative exponent. Remember what happens with negative exponents? They go into the denominator to become positive. So this is not in this form for the same reason that the one above it wasn't. Not exactly the same reason, sorry, I shouldn't have said that. Okay, last one of these, initial value would be 3, base would be 4. Yes or no? No. Should have said no here. Again, exponent, I'm just, write what you want here. Exponent, not a unknown variable is a way of saying it, right? It's confusing because remember, we can see lots of different letters there. We've been seeing an N there for the last few days. It could be an X like it is today. It could be lots of letters. It won't be E. E is special, reserved for that 2.71 ... number. Okay? Good? All right, without a calculator, we're going to do some computations. We've got to be able to do some math without a calculator. Here's some practice of it. because there's parts of your test that you don't have a calculator. So we got to be ready for it. Here's an example of why you need to be ready. So I'm going to plug in, it says x is 2, in for x, right? So clearly I get 3 to the 3rd power. And how do I do this by hand? Well, let's remember order of operations. We don't do 6 times 3. We do 3 to the 3rd and then times 6. So 3 to the 3rd is not 9. 3 to the 3rd is 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27, right? We'll see. So we get 27. And yeah, oh my gosh, when's the last time you had to do something like this? 6 times 7 is 42. Carry the 4. 6 times 2 is 12. Plus 4 is 16. So when I plug 2 in, I get 162. Good? Okay. Something we haven't talked about this year together. Hopefully your Algebra 2 teacher talked about it. If you had me, I know I did. But let's see what this one's looking like. I'm going to plug in a fraction as an exponent. So fraction exponents, of course we could put it in our calculator and get our answer, but you could, this is a type of question you could get without a calculator, okay? So let's go off to the side and let me remind you how to do fraction exponents. Fraction exponents can be written as a radical, okay? So you are going to write 8 under the radical, okay? That's the number inside, and the 1 and the 3 have special places that they go. The denominator is 3, it is your root, and the numerator is 1, it goes on this number. My students might remember I would put right over left, hug somebody, so if you make the fraction, there's a reason I'm telling you that. Fraction of right over left, 1/3, and if you hug somebody, you open your arms like this, right? Right over left, hug someone. 1 goes over here, 3 goes over here. So that can help you remember, like, where the numbers go, okay? And so what you're asked, and I have seen people during tests doing this. They're like, looks like they're dancing. They're like, oh, in Algebra 2, really. But anyway, cube root of 8 is what? 2. 2 times 2 times 2, okay? So we get -5 times 2 is -10. So, wait, say it again? Because 2 times 2 times 2 is 8, and we can write that as 2 to the 3rd power. That's what it's saying. What number, when I multiply it 3 times, gets me that? Okay? I get paid the big bucks. That's why. I heard it. Thank you. All right. Here we go. The next couple examples, I really like these problems. Okay, we're going to write an equation in this form, shocker, given some information, okay? First thing is the value of g at x equals 0 is 3. That's code for your y-intercept, okay? So that's A. A is 3, right? When x is 0, y is your y-intercept, okay? And it says that the output value of g doubles at every 1 unit increase in the input value. So here's our input values, increasing by 1, 1, 2, 3. And if we're going to double these, what are we doing? What does that mean mathematically? Times 2. So 3 times 2, 6 times 2, 12 times 2, 24 times 2. And that makes our b value what? 2. What are we multiplying by each time? So g of x is, there's my a value, my initial value, my a sub 0, my y-intercept, whatever you want to call it. And then there's my growth factor. It's getting bigger. We call that growth. That's it. Right? Last page, same type of problem as example 5, is the same type of problem as we just did. But now we're just given a table of values. Guys, this is what you just did yesterday. We called it a geometric sequence yesterday. Now we're calling it an exponential function. Okay? So, I just want to make a point real quick. If this was adding 2 every time, if I was adding 2 as I went through the chart, what would that make what kind of function would this be? It would be linear, right? And that would mean my slope was 2. Okay, so you're going to have one in your homework where you're not multiplying. We slipped one in there where it's adding. That's arithmetic, also known as linear. Okay, y-intercept would be 3. You would write it as 2x plus 3. Right? There's my slope of adding 2. There's my y-intercept of 3. Okay, look at this next one. I'm going to write in this form, which means for each of these, I need an A and a B. Right? Let's get set up. A is my y-intercept. A is what y is when x is 0. If you remember yesterday, it wasn't even given to us. We had to go backwards in the chart to find it, which could happen on one of these, okay? But here, it gave us the y-intercept. Thank you very much. We have to know that A is the y-intercept, or A sub 0. What are we multiplying by as we go through this first one? 2. What if I didn't know what it is? Remember how we found R yesterday, which is the same as B? You could take any 2 consecutive numbers, right to left, and divide it. So if I'm dividing by 2 right to left, I'm multiplying by 2 left to right. And you can see that here, okay? So write that in the correct form. There we go. 2 is a growth factor. Okay, I just want to remind you of that. Anytime your B value is greater than 1, you are growing. And look at your Y's. They're getting bigger as we go left to right. Okay? In this one, what are we multiplying by as we go left to right? 1/2. So take any 2 numbers consecutively, 10 over 20, 5 over 10. I'm not messing with the fractions. That gets me 1/2. Or 0.5, right? Not -2. You're thinking of adding and subtracting. So you can use 0.5 or 1/2. It doesn't matter. And this is a decay factor. It's getting smaller. The numbers are getting smaller. Our B value is less than 1. Okay. Last example. Cross out those directions. I don't even know what she's saying there. We're going to sketch this graph. And we're not making XY charts today. We're not graphing like perfectly. Sketching a quick graph is all we need, okay? So we have A is 3, B is 2. A is my y-intercept. So 1, 2, 3, there she is. And since B is greater than 1, that means it's growing, right? It's a growth factor. So what would that look like on my graph? Really easy. My numbers are starting small and getting bigger as I go left to right. Are those the exact points? Nope. It's a sketch. Don't forget, we have an asymptote right here at y equals 0. Let's go ahead and fill that in. And let's do that end behavior. Notice the order they're doing this in. They put the positive infinity first. So just always read it carefully. Okay, so it's saying as x goes to the right, our y values are going up forever, right? And as our x values go to the left, what are our y values going towards? 0. Good. Domain on all of these are all real numbers, negative infinity to infinity. Sam, what's the range? Good girl. Yeah. Yep. From 0, not including it, to infinity. Last one. Did I lose you, Lily? Okay, sorry. Okay. I just want to make sure I didn't ignore you if you had a question. Initial value 5, decay factor, right? Because it's less than 1 of 1/2. So A is my y-intercept, and it's decaying, so it's getting smaller as we go left to right. So I'm going to start big and small. So it goes the other way with that asymptote at y equals 0. So as we go to the right, what are our y values approaching? 0. As we go to the left, our y values are approaching positive infinity. I feel like I'm going really fast here at the end, so if I went too fast on any of this, we're done in a second. I'll be walking around. Call me over and have me explain it to you better. Domain on all these problems, negative infinity to infinity. Negative infinity to 0 would mean these points. This is still 0 to infinity, okay? Always least to greatest, too. Good? That make sense? Mm-hmm. So guys, B5 is on page 30. Everybody have it written down? Can I? Is Raja still writing? So the first 4, just put it in your calculator. Can I put these in my calculator correctly? That's the question. Sam, you were asking yesterday.